Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll continue this topical MCQ on topic 4, which is on states of matter, as well as the gas laws, which involve the Avogadro's law, Charles' law, Boyle's law, and of course the ideal gas law. So starting off, which statement explains why the boiling point of methane is higher than that of neon? So when we have methane, we have CH4. I've drawn the as tetrahedral. So two are in the flat in this paper, in this screen. This is coming out, pointing to you, pointing at you, looking at you right in the eye. This is going away from the screen, behind the screen, away from you, okay? So these two are not in the plane of this paper or the screen. One is out, one is in. And of course, there's 109 degree tetrahedral. You have 4 atoms that are the same around the carbon. This is actually a non-polar molecule. When you have neon, it's just existing as a single atom. This is called a monatomic, or you can call them monoatomic because they exist as just single atoms. They don't form covalent bond with each other. They are happy with 8 electrons in the outer shell as a noble gas. So what happened then is, why is it that this has a higher boiling point than this? Since this is non-polar and this is also existing as a single atom, we are just comparing the strength of their van der Waals. The strength of van der Waals, the most important thing is the total number of electrons in the molecule or the atom. But the second thing that some students don't know is to do with surface area. So between this and this, you can see that they purposely give you neon having 20 electrons. And CH4 having, hang on, it's not 20 electrons. If you look at periodic table, it has 10 protons, therefore 10 electrons. If you look at this, there's 6 proton there, and 1 proton, 1 proton, 1 proton, 1 proton. So altogether there are 10 protons, so there are 10 electrons. So you see they have the same number of electrons, so you can't exactly use that first factor, can you? Okay, well, I don't want to highlight that. You don't want to use that factor because they have the same number of electrons there, alright? So what essentially happened is you can think about the CH4 having more atoms. They will have a bigger surface area than neon. Therefore, CH4 will have stronger van der Waals than neon, alright? So in fact, molecules of methane have a stronger van der Waals due to the bigger surface area than that of neon. It's got nothing to do with polarity because the molecule of methane is non-polar. It doesn't form hydrogen bond, and this thing is incorrect because van der Waals does not depend on molecular mass. Van der Waals depend on this, but also depends on this as part of your structure and bonding case study. In this next question, we have some more questions on structure and bonding. They give you the Ionic Radii of these particular cations and anions. So it's saying that cesium chloride, which is cesium, oops, no, I don't want that. Cesium chloride follows that, but sodium chloride and magnesium oxide. So, I don't know, sodium and magnesium. So how we can tell that cesium is way bigger? So the radius of cesium is way bigger than sodium and magnesium. Of course, the chloride will be the same in both cases. So we're not really talking about the difference in the anion. We're talking about the difference in the cations. But there's nothing to do with the cation here. It cannot be the charge because cesium is also group 1. Na plus is also group 1, so it can't be the charge. It's got nothing to do with the sum of the ionic charges because, you know, we have got, when you look at this, NaCl and MgO, you have Na plus and Cl minus, you have Mg2 plus and O2 minus. If you talk about the sum of the ionic chain charges, then it doesn't add up that these two have the same structure. So we're down to B and C. As I mentioned earlier, it seems that the ionic radius is the more important factor rather than the ratio of the ionic charges. For the same reason again as I mentioned for option D, you see the ratio of the ionic charges is 1:1. Here is also 1:1, but you also have 1:1. So if you compare if you compare cesium is to Cl minus 1:1 versus Na plus is to Cl minus is 1:1, they have the same charge ratio, they have the same ionic charge ratio, but yet cesium chloride and sodium chloride have different structure. So it can't be the ratio of the ionic charges, they are important, which leave us by elimination. The ratio of the ionic radii is actually the more important concept, and I managed to get that by eliminating the ones that do not make sense at all, simply by this observation. Moving on to the next question. So this is about the gas laws. They're saying that which gas closely approaches ideal behavior. So you want ideal behavior. So we talk about assumptions of ideal gases, which they like to ask in theory paper. But of course, it's about the application of these assumptions that matter. So we said that the most important one is negligible intermolecular force. That is probably the most important one. Negligible intermolecular forces. So you want the weakest intermolecular force. You don't want hydrogen bond if you want it to be ideal. NH3 can form hydrogen bond. Okay, so that one is approaching non-ideal out of all of this because that's the strongest intermolecular force. None of the other one can form hydrogen bond. Between carbon dioxide, helium, and oxygen, you can think of them in terms of other intermolecular force. So first of all, you have hydrogen bond, as I mentioned already. You also have permanent dipole. And of course, you have van der Waals as well. Out of all of these, you don't have permanent dipole because this is bonded to itself, so this is non-polar. This is non-polar because the dipole there get cancelled out by the dipole there. So this is a non-polar molecule. So we're not looking at that. We're just looking at van der Waals. Van der Waals depend on total number of electrons in the molecule or in the atom, and it also depends on surface area. Okay, but just looking by the total number of electrons, I hope you can see that helium only contains 2 electrons because it's got 2 protons. This is the one with the lowest number of electrons without even counting for the rest. Okay, so helium has got the lowest number of electrons in the atom. It's got the weakest van der Waals. It's got the most negligible intermolecular force. It's the one that will behave ideal the most. Moving to this next question. So we are saying that in which change do you only need to overcome van der Waals? Only van der Waals. So when you talk about evaporation of ethanol, so if you draw out ethanol, I hope you can see that ethanol can form hydrogen bonding. You have a hydrogen bonded to a highly electronegative oxygen. So you got lone pair there. And then you can have another ethanol molecule like that. So delta plus, delta minus. We show dipoles. We show dipoles, delta plus, delta minus. We show the lone pair on the electronegative oxygen, forming the hydrogen bond with the neighboring molecules, because hydrogen bond is an intermolecular forces. So when you evaporate ethanol, you need to break strong, well, I guess just break hydrogen bond. It is stronger than permanent dipole, but it's not as strong as covalent bond. Melting of ice. So we know ice again. Ice under states of matter is your case study. So it's a hydrogen bonded solid. Hydrogen bonded solid. That is your ice. So you need to break the hydrogen bond again. I hope you know that in ice you have a very special structure because the molecules are so close together that that this one become 109 degree because of the very strong hydrogen bond in ice. So dipoles, lone pair and level, and become more like tetrahedral because these are very close together, that these become as strong as a covalent bond, but they're obviously still hydrogen bond. That's why you need to break when you melt ice. Okay, when you melt solid carbon dioxide, carbon dioxide is non-polar molecule. because the dipole there get cancelled out by the dipole there in opposite direction. And because these are oxygen, the magnitude, the value is equal, but they are in opposite direction, so they cancel out. This is a non-polar CO2. You only break van der Waals. So we got our option there. And of course, when you solidify butane, this is liquid going to solid. You make the liquid molecules pack closer together. So you will form van der Waals. Okay, whereas you want to overcome, you want to break van der Waals. You don't want to form van der Waals. This is the last question of this 5-question series. So they're asking what could be the identities of R, S, and T. If you look first of all at the electrical conductivity when they are solid, so those are poor, but this one is good when it's solid. So SiO2 do not conduct, so it has to be graphite for T. So we are left with just 2 options, all right? And then between R and S, you see that you only have NaCl versus MgO. So both are giant ionic compound. They have giant ionic structure. So we need to consider breaking the strong ionic bond. So what is the difference between the ionic bond between these two? Well, you can see that you have a higher charge cation. You also have a smaller cation. I hope you know that ionic radius, which you do from topic 2. So across a period, so from sodium to chlorine, it decreases in atomic radius. And then you also learn that the ionic radius also decreases. And by the way, these data are given for free in your data booklet. But of course, you need to know the trend. Otherwise, you'll be wasting time looking through the data all the time. So magnesium 2+ is smaller than Na+. It has a higher charge cation. All right. That is just the cation. Okay. We haven't even talked about the anion yet. If we talk about the anion, then we also have O2- is higher charge than Cl-. And of course, O2- is smaller than Cl-. So if you know O2- is in the second shell, Cl- is in the third shell, one additional shell, obviously bigger than that, yeah? So again, that is the anion. So both the cation, higher charge, smaller size. So the cation is a higher charge density than Na+. The anion, higher charge, smaller size, also higher charge density than the Cl-. So we can think about MgO, it has a stronger ionic bond because the charge density of the cation and the charge density of the anions are bigger than that of Na+ and Cl-. So you get a stronger ionic bond. Therefore, we need more energy to break it. Therefore, we need a lot higher melting point and also boiling point that refer to being MgO instead of NaCl. Okay, so I hope that makes sense. In a theory paper, you'll be expected to outline all these different factors, and it will make more sense when you cover lattice enthalpy, which is to do with your strength of ionic bond when you reach A2 energetics under lattice energy, lattice enthalpy. This is it in this 5-question series. If you enjoyed this tutorial, don't forget to subscribe, click the button on the bottom right, and share the channel widely with your friends, your class group chat, your social contact, which is probably far more extensive than mine, your teachers, your whoever else you think these videos might be useful for. And thank you for watching. I'll see you in the next video.